So I mentioned there's 5 problems left relative to this chapter. So I'll just show you the things we're going to do. Here we have a backhoe. We have an engine support. We're going to look at a pipe wrench. That'll set up just what I'll call move this up, a funky wrench, kind of strange looking. And then we have, moving this down, the following. This probably is best called a doohickey, okay? So it's a lift mechanism here. All right. So let's start with our first problem we're going to be taking a look at. Make sure I got everything lined up. Okay. So we're looking here at the backhoe. So in this problem, we have a hydraulic cylinder that's going to provide a push. So let's just take a look at this thing. So if we look what we have here, here's this bucket. And so there's a big support rod here that has a rod go out here. But the bucket, all right, is pinned to this lower rod right there. And then this hydraulic cylinder pushes out this way, as it were, okay? And by doing that, that moves this down, and this rotates about this point D. This is a rod here. And then that causes this force to be pushed down into here, which then makes the bucket stay level, as it were, as opposed to coming down, okay? So we can see how it works. And so the question is, this is a loaded bucket. It has 1,200-pound load in it, where the center of gravity is here at G. Okay? And we want to find what is the push of the hydraulic rod, what is the force in AD, and what is the force in this member here, A to C. All right? And we're going to treat A to D and A to C as 2 force members. So their mass relative to the overall weight of everything else in here is negligible. Okay, so we have 2 force members. That means the force goes along a line AD and a line AC. So that tells us a lot about how things are oriented. All right? Okay. We'll come back to these pictures one by one. And so here we have this problem. So here's our cylinder coming down at 45 degrees. Here's our 2 force member. So we have this long support piece here. And so here's this pin that was in that support piece going. Here was AD coming across. And then here's AC, which will, if you think about it, this pushes here. That'll rotate that around. And then that force will drive down into here. And that'll cause the bucket to stay up. All right. Weight of the bucket with its load is 1,200 pounds. Center of mass of all of that is at G. Find, it says FAB, AC, AD to hold the bucket. All right. So, we need a free body diagram. We'll start right here with the bucket. All right. Now, we were asked for this, that, and that. So, let's ask the question, do I care at all about the forces here? No. Problem didn't ask for it, so you shouldn't care. So here's what we're going to do. We're going to sum the moments here at E, okay? And that means all the forces happening right here, all we have is then the weight there and the push right here. So that'll allow us to solve for this force. Then we can come and look at this joint, and we can solve everything immediately. So this problem by itself looks kind of intimidating. It's really not. So here's our free body diagram of the bucket. We have our 1,200-pound load. We're going to have the forces at the pin, which we don't care about. And this is a 2 force member, so it's very apparent that the force is coming down, and that's because that will then rotate about that pin and enable that bucket to stay up. So this force can't be going out that way. It's got to be coming down. And we know the orientation relative to E, it is 1 foot up, the angle there being 60 degrees. And then the distance from here to there to line up with this, that's 1/4 of a foot. So we're ready to go. So we can sum the moments at E, which must be 0. Okay, so we have relative to E, this is a vertical force. We only care about the horizontal distance. So that's 1.5 feet to get over there. And that's wants to go clockwise. We have minus 1,200 times 1.5. All right, now we have AC. So if we were to look at the vertical portion that's coming down, all right, and then we have that horizontal distance, that'll be going counterclockwise. So that'll be plus FAC sine 60 there and 0.25 for the separation or horizontal distance. Now we're going to take, if we take the horizontal portion going across here, and that's 1 foot away, that again would go counterclockwise. So we have plus FAC cos 60 times 1. And bam, we're all done. It's just solve for FAC. If you do that, you wind up with FAC is 2,512 pounds. And there you go. All right, so now we can just come back, go up to here. All right, so at the other end of FAC, we have the pin where everything came together. We'll just bring that down real quick. So we have the force going down here means that this is pushing back up equal and opposite. So we have a force coming up into that. All right. Now I will comment is once you've done, if you know that, since you know this pushes down, we have the equal and opposite coming up, that alone means that FAB must be pointing down. Because if this goes up, this is horizontal, that's got to go down to balance it. Then you're left with this has got a leftward component, that's got a leftward component. That means this one's got to go to the right. So the free body diagram from this, there's really no reason when we solve this problem you should go, oops, I guessed wrong on the direction. It's apparent. Okay. So given this, knowing FAC, if we sum forces in the y, we get FAB. Then sum forces in the x, we get FAD. So you would have this. Summing forces in the y, we know that's equal to 0. So this is 2512. And then we need the sine of 60. And then we'd have minus FAB, sine of 45. And that's it. And that leaves us FAB at 3076 pounds. Summing forces in the x, we would have minus 2512 cos 60 and minus 3076 cos 45 plus FAD, set that equal to 0. FAD equals 3431.72 pounds. And there's the end of the problem. So, really quick problem to pull off. Though the picture, to start, kind of looks kind of ugly. All right. Our next problem. So, we have an engine here, which we're told is 125 kilograms. And the question for this problem, there you go, is find the load in members DB and FB. So here's DB and here's FB. We're asked to find the load in this hydraulic support and in this two-force member. And both the hydraulic support will obviously also act as a two-force member, just force along the connections here. Okay? So, now, let me just comment here on, go back to this one for just a moment. Notice what we did here. When we solved this problem, we started from what we knew. So we knew we had 1,200 pounds, and we just kind of worked our way back to the things we wanted to figure out. That's usually the best way to attack these problems. Sometimes it's better to do other stuff, but usually that's the best sense. So what I have in this problem is start from what I know. Well, I know this is 125 kilograms since I know its weight. And so I know stuff here, and so I'm going to use that to go back in through the machine. So it's the same approach to solving it. I'll just note that real quick here. All right. So here's the basic picture. I've just taken the engine out and replaced it with its weight. 125 times 9.81. And so what I'm going to do is I'm going to remove this bar and make a free body diagram. So here's this bar. All right, here's the engine coming off of it. If we go look at the geometry, basically this is up 3 meters and over 1 meter. So that's what that's showing. So that's a 1, 3, the square root of 10 triangle. All right, and then on the other end of this bar is this pin joint here. So I have the forces for EX and EY sitting there. All right. So, and how did I draw this? Well, look at this. If this acts as a fulcrum, as this goes down, it means this end is going to want to go up. So EY obviously has to be pushing down this way, or this thing has to be pulling it down. And if this is a little to the left, that's got to be to the right. So that's how the logic behind why I drew what I drew. But this is definitely a case, no big deal. If you put EY up, so what? The signs actually will work for you. You'll get a negative and it will be fine. Okay, so I need to figure this out. It says find FB. All right, so if I take the moments right here, and I don't care about these things, I have that. I'll figure that out very, very quickly. So sum of the moments at E, which will be equal to 0. I have this thing, and this is 1, 2, 3 meters out. So 125 times 9.81 times 3, and that's counterclockwise. And this is, if I look at the X component of this force, that's aligned with E, so that does nothing. I only need the Y. And if that's coming up relative to here, that's clockwise, so it's going to be negative FFB. I need the Y component, so that'll be 3 on the root of 10. So that's all of the force, and it's 2 meters away. Again, set that equal to 0. Solve for FFB. Come up with 1,939 newtons. So there we go. We just knocked off, bring this down for the problem, we just knocked that piece off. All right. So how would I attack the next part? Well, let's just look at the pieces I have. Here's what makes sense to me. Now that I know what FFB is, I can sum forces in the X and Y here, and I can get EX and EY. And I'll note, if you do that, I'll let you sum forces. It's very easy to do. But EX would work out to be 613 newtons, positive, so I guessed in the right direction. And EY also works out to be 613 newtons. Again, positive, so the right direction. So what does that mean? It says this piece down here is pulling down on this one. It's pulling it over this way. Well, that means this piece is pulling up on this one and pulling over this way. Equal and opposite. When you do a free body diagram, when I drew these in, that was a free choice. But the moment you draw those in, you draw these in too, going the opposite way. That's not a free choice. Pick one, that determines the other. All right. So, knowing got the moment, now I sum and got these. Well, now I know these. So knowing these, let's look at the situation. Do I care about C? Nope, not at all. So I'll sum the moments at C, and that'll give me this FDB right away, and zip, bam, boom, problem's going to be knocked out. So we go right over here. We sum the moments at C, set that equal to 0. That's all fine. EY is lined up with C, so that means it does nothing. Let's see, we got 2 meters here, 1 meter there. So EX is going counterclockwise. So we have EX times 3 away. All right. The Y component of FDB is aligned here with C, so that does nothing. I only need the X component. So let's see, that is, and that's going to go this way, so that's clockwise, so I need a minus FDB, and I'm looking for the X component, so I'll take the sine of 45, though it doesn't really matter, because you can be in this side and take the cosine. It all works. Okay, and that'll be 1 meter away, and solve for FDB, and you would come up with 2601 newtons. And that finishes off this one. So we can just cross that off, and that's all finished. And I'm just keeping track of my numbers as I go through. All right. This will be a little longer video, but let me just set up here. We're going to do a third problem in this video. We're going to take a look real quick at our little pipe wrench here. This is one that, quite frankly, we could have done this really in Chapter 5, but it's in the book, actually, a former edition. This is in the book in Chapter 6, so that's why we're doing it now. So we're going to look at the loadings on this, and I'll see you back in just a moment while I get set up. All right, for those of you that haven't used a pipe wrench before, it's a fairly simple device. You have your pipe that's coming through here, and this is a very sharp cutting wheel. Off many nice ones, this is a diamond cutting wheel. And what happens then is you take this and you twist it, and this puts pressure on by this wheel on the pipe. And then what you do is you just literally you get it really tight, and then you take this, hold the pipe below, and you twirl this around the pipe, and it scores the pipe. And so first it's a little hard to run, but as you go around a couple of times, it gets real easy. Then you twist it down a little further, and you do it again. You twist down a little further and do it again, and pretty soon the pipe just falls off. Okay, so that's how that works. So for this problem, we're going to have 80 pounds of 80 newtons, excuse me, of force being applied by the wheel to the surface of the pipe. These things here, these are not cutters, these are rollers. So as this thing rolls around, this thing cuts, and these things are just wheels to hold the pipe in place, keep things oriented as it you twirl it around the pipe there. All right, so let's go to the next picture that just has the geometry laid out. We're using our normal XY coordinate system. We have 80 pounds through the 80 newtons, excuse me, through the wheel coming in. Here's our pipe. The outer diameter of the pipe is 10 millimeters, and the radii of these rollers, okay, is 7 meters. So that says from here, that's 10 plus 7, so we have 17 millimeters there, okay? And the way that's oriented, so here's the center line, then to get up to there, there's 10 meters there. So that tells us, so we have 17, 10, we have a little triangle in here. That's what I have here. So we can get that angle is 36 degrees. We'll note that. If you look at the symmetry of this situation, there's 80 pounds here. The orientation of these rollers is identical. So by symmetry, whatever force is in FB is in FC, or vice versa. So we have that. All right. Well, given all of that, how would you solve this thing? Well, since these are equal by symmetry, really this is a ridiculous problem. I have no idea why this wasn't in Chapter 5. But, I mean, it is a machine, as it were, but it's pretty simple. So we have 80 newtons going in a positive direction. FB and FC are equal, so I'll just say minus 2FB, and this is 36 degrees, cos of 36.03 degrees. Set that equal to 0, solve for FB, and I could have written 2FC here if I wanted, whatever. We get 49.46 newtons. And that one's done. All right. We're gonna end the video right here. We have 2 problems left to go. That'll finish this chapter, and as I generally do, I leave the best for last. See you soon.